So this is our Honors Chemistry Section 10.2 lesson video, and so we're going to continue to talk about the mole. And so if you watch the Section 1 video, we learned about 1 mole and how it's related to Avogadro's number. It's 6.02 times 10 to the 23 represented particles, and we said those particles could be atoms, molecules, or ions. And then in Section 1, we also learned how to calculate the molar mass. So now we're going to continue with molar mass. And so you can actually use the molar mass of a substance as a conversion factor to convert between moles and mass. So since we know when we do molar mass, it's grams per mole, that means that's the grams in 1 mole of the substance. So now we have a second conversion factor to use for the mole, and that is 1 mole equals molar mass. And so we use this one if the question says anything about grams or mass. So let's look at what one might look like. So it says, what is the mass of 9.45 moles of aluminum oxide? Well, the problem is with molar mass is every substance is going to have its own number. So like in 10.1 when we did the 6.02, that number was the same for every single problem. But when you're doing molar mass, each substance is going to have its own molar mass. So you got to be careful and make sure you're writing the formula right and adding up the mass correctly. Let me grab a calculator real quick. All right, so let's go ahead and start on this one. So it says, what is the mass of 9.45 moles of aluminum oxide? So first I need to figure out what the formula is. So aluminum is Al, it's in group 13, so it has a positive 3 charge. Oxide is just oxygen, and it has a negative 2 charge. So of course I need to balance my charges by putting a 2 and a 3, so they both are positive and negative 6. All right, so I start with what I know, and I know I have 9.45 moles of aluminum oxide. And so I'm trying to get to the mass or to grams. So that's how I know I'm using the molar mass formula and not the 6.02. If they'd asked me about atoms, molecules, or ions, I would use Avogadro's number. But since they asked me about mass, I'm going to use the molar mass. So I have to add up the molar mass of Al2O3. So aluminum is about 27, but I'm going to multiply that by 2 because there are 2 aluminums. And oxygen is about 16, but I'm going to multiply that by 3 because there are 3 oxygens. So once I do that, I get a molar mass of about 102 grams per mole. So the grams per mole, what that's saying is I can use this formula and say 1 mole equals 102 grams for aluminum oxide. If it was any other substance, it will have a different molar mass. So once I know 1 mole is 102 grams, I just need to follow the golden rule. So since mole is on top, I'm going to put the 1 mole on bottom. And then I'm trying to get to mass or grams, so I put my 102 grams on top. So my moles cancel. And then since both numbers are on top, I'm just going to multiply, and so I get 963.9 grams of aluminum oxide. Now, you'll get to the point where you don't need to write all this out. You'll just do this in your calculator and you'll just plug it in. But in the beginning, you may need to actually write out the conversion factor. So like I said, what's different in this conversion factor and the one from section 10.1 is 10.1, the number remains the same every time. In molar mass, you're going to have to add it up. So that's where you can see if you get the wrong formula, you're going to get the wrong molar mass. And then, of course, you're going to get the wrong answer. So you got to be super careful on getting the formulas correct on these. All right, so let's look at another one. So it says find the mass in grams. So again, once I see words like mass and grams, that's how I know I'm using molar mass and not Avogadro's number. Of 4.52 times 10 to the negative 3 moles of C20H42. So see, this time I gave you the formula. However, most times you are not that lucky. It'll look like this, iron 2 hydroxide, and you have to write it yourself. All right, so I start with what I know. So I have 4.52 times 10 to the negative 3 moles of C20H42. So I know I'm going to need molar mass, so let me go ahead and add up C20H42. So C is about 12, but I'm going to multiply that by 20. H is 1, and I'm going to multiply that by 42. And so once I did that, I got about 282 grams per mole. So remember, y'all, what that means is 1 mole equals 282 grams for C20H42. So I follow my golden rule. Mole's going to go on bottom. So remember, molar mass always equals 1 mole. So 1 mole equals, and then I added up that it was 282 grams. So my moles cancel. Since both numbers are on top, I'm going to multiply. And so I ended up getting 1.27 grams of C20H42. And so that's all you have to do. It's just following the golden rule, just like in 10.1, except this time because molar mass is different for every substance, I need to add it up. All right, so let's look at this one when I give you the name again. Because remember, if you don't get the formula right, you're going to miss the problem. So it says calculate the mass. So of course, once I see mass, I know I'm using molar mass of 2.5 moles of iron 2 hydroxide. So we haven't done a Roman numeral in a while, so let me remind you how to do that. So iron is Fe. The Roman numeral indicates the charge, because remember, iron can have multiple charges. It's a transition metal. Hydroxide's OH, that has a negative charge. It's on your polyatomic ion sheet. So I need to cross the 2 down. Remember, even though hydroxide does not already have a subscript, it is a polyatomic ion, so you do need to put it in parentheses. That's the most common one people forget parentheses on. If you forget parentheses, you're going to get the molar mass wrong. All right, so we're starting with 2.5 moles of iron 2 hydroxide. So of course I know that 1 mole is molar mass, but I need to add up to figure out what molar mass is. So Fe on the periodic table is about 56, O is about 16, but I do have 2 oxygens. Remember, the 2 goes to anything inside parentheses. H is 1, but I also have 2 of those, and so I get a molar mass of 90 grams per mole. So remember, what that means is 1 mole is 90 grams for iron 2 hydroxide. So I follow my golden rule. Mole is going to go on bottom, and it's 1 mole every time for molar mass. So 1 mole equals, in this case, 90 grams. So my moles cancel, and then since both my numbers are on top, I'm going to multiply, and I ended up getting 225 grams of FeOH2. And don't forget, if you don't know what your units are or what you ended up with, especially when we get to like multiple steps, it's always your last unit on the top that you haven't canceled out. All right, so maybe pause the video, try the next one, and then I'll assume you've done that. We'll look at it together. So it says calculate the number of moles in 75 grams of dinitrogen trioxide. So the fact that I see grams right here, that's how I know I'm using molar mass and not Avogadro's number. So I'm going to start with my 75 grams. And then let me go ahead and write my formula. So since I see prefixes, I don't have to do anything with charges. So dinitrogen is just N2, trioxide is O3. So I'm starting with 75 grams of N2O3. So I know 1 mole equals molar mass, so let me go ahead and add up molar mass for N2O3. So N is about 14, but I'm going to multiply it by 2. O is about 16, but I'm going to multiply it by 3. And remember, y'all, these numbers, I'm just pulling the masses off the periodic table. Those are the bottom numbers on the periodic table. So once I add that up, I get about 76 grams per mole. So what that means is 1 mole equals 76 grams for N2O3. So then I follow my golden rule. Since I have grams on top, I'm going to put my 76 grams on bottom and my 1 mole on top. So my grams cancel. Now, a lot of you, when you try this one on your own, you put the grams on top because you just saw me do that twice. Well, I put my grams on top because I started with moles. So my mole had to go on bottom. However, in this problem, you're starting with grams. So your grams have to go on bottom. It's all about following the golden rule every single time. All right, so once you divide, clearly you're going to get slightly less than 1, so I just put 0.99 moles of N2O3. Okay, so y'all, whenever you're deciding what goes on top and goes on bottom, don't look at what did I do, look at what are you starting with, and follow the golden rule. Because if I give it to you the opposite way, you're going to need to do it opposite than what I did. All right, now sometimes though, you are going to need to use more than one of the conversion factors. So I'm going to show you now some that do a combination of the one we just learned, 1 mole equals molar mass, and the one we learned in section 10.1, which is 1 mole equals Avogadro's number. So let's look at some of those. So this one, it says, how many glucose molecules? So once I see molecules, that makes me think, okay, I'm going to use Avogadro's number. Are in 5.23 grams of C6H12O6. Once I see grams, I know I'm using molar mass. So for this problem, I'm going to need to use both of them. All right, so we start with what we know. I know I have 5.23 grams of C6H12O6. So since I'm starting with grams, I know I'm using this one first. 1 mole equals molar mass. So the first thing I need to do is add up the molar mass of C6H12O6. So carbon is about 12, but I'm going to multiply it by 6. Hydrogen's 1, I'm going to multiply it by 12. Oxygen's 16, and I'm going to multiply it by 6. And so once I do all that, I end up getting about 180 grams per mole. So what that means is 1 mole equals 180 grams. So then I follow the golden rule. I have grams on top, so I put my 180 grams on bottom. Remember, the golden rule is how you know what goes on top and what goes on bottom. That equals 1 mole. Because, of course, molar mass always equals 1 mole. So my grams cancel. Now I've made it to moles of C6H12O6, but it didn't ask me for moles. It asked me for molecules. So that's where then I'll use this formula or this conversion factor right here for Avogadro's number. So I can see that mole is on top, so I'm going to put the 1 mole on bottom. And that's going to equal 6.02 times 10 to the 23 molecules of C6H12O6. So see, now I know, that's how I know when I can put my equal sign. Is see how now I have molecules of C6H12O6? Once you get what they're asking for, that's how you know you're done. It might take multiple steps for you to get there. So I'm going to multiply my two numbers that are in the numerator, and I'm going to divide by 180 because it's in the denominator. And so when I do all that, I get 1.75 times 10 to the 22 molecules of C6H12O6. Okay, so that's what it'll look like if you need to use both. Now, you can hopefully you can obviously tell that you could have shortened this into one step, because since molar mass equals 1 mole and 6.02 times 10 to the 23 equals 1 mole, that means these equal each other also. So your molar mass is 6.02 times 10 to the 23 molecules. So what you could have done was put your 180 grams on bottom and your 6.02 times 10 to the 23 molecules on top, and then you would have gotten it done in one step instead of two. However, a lot of times when I try to consolidate steps, it confuses some people, so that's why in class you'll always see me break it up as 2. But remember, in math there's always more than one way to do it. Just make sure whatever way you pick is correct every time. Alright, so, and if you ever find your own way to do it, please check with me to make sure that it does work every time, because I'll let you know, like, okay, this one's not going to work in these situations, and so don't use that one. Alright, so the next one, it says how many oxygen atoms are in the sample above. So this is where I'm now going from molecules to atoms, but it only asks me about atoms of oxygen. So what I can do is I can look at C6H12O6 and realize, okay, well, one molecule of C6H12O6 has 6 atoms of oxygen in it. So in other words, and again, y'all, I'm going to write out the whole thing, but y'all will probably just do this in your calculator. You'll just take this number and multiply it by 6. Which is, of course, more than fine, but I'm going to show you, of course, how you would write it out completely since I'm the teacher. Alright, so I take my original molecules that I just calculated, and so then I'm trying to get from molecules to atoms of oxygen. So I follow my golden rule, and my one molecule is going to go on bottom, and one molecule of glucose has 6 atoms of oxygen. So I'll put my 6 atoms of oxygen on top. And again, if you get to the point where you can do all this stuff in your head or in your calculator, that is fine. Alright, so I end up getting 1.05 times 10 to the 24 atoms of oxygen. Now, of course, if you're watching this and you're not in my class, you would need to check with your teacher as far as do they require you to show your work or not. Alright, so this is what you do when you need to use multiple different steps, which is a good introduction for us to get to chapter 12, because in chapter 12 we have to use a lot of multi-step problems. So now that you saw me do one, I want y'all to try the next one. So maybe pause the video, try it on your own, and then we'll look at it together. Okay, so I'm going to assume you've already paused it and tried it. And so let's look at the first part. So it says, how many nitric acid molecules are in 4.2 grams of HNO3? All right, so again, I see molecules, which makes me realize I need to use Avogadro's number, but I also see grams, which makes me realize I need to use molar mass. So I start with what I know, and that is that I have 4.2 grams of HNO3. All right, so first step is I'm going to use my molar mass to get to moles, but I have to add up the molar mass. So H is 1, N is about 14, O is 16, but I'm going to multiply it by 3. And remember, y'all, I'm just pulling these from the masses on the periodic table. And so once I do that, I get about 63 grams per mole. So what that means is 1 mole equals 63 grams or HNO3. So then I follow my golden rule. I have grams on top, so I put my 63 grams on bottom, and that equals 1 mole of HNO3. So see, we got away from grams, but the problem is they want me to get all the way to molecules, so I'm going to have to do another step. And that's where Avogadro's number comes into play. So I just follow my golden rule. I have moles on top, so I'm going to put my 1 mole on bottom. And then I know how much 1 mole is 6.02 times 10 to the 23 molecules. So I'll put that on top. And again, you're more than welcome to do this in one step if you prefer. They both give you the same answer. So I'm going to multiply my top two numbers and divide by the 63. And so when I did that, I got 4.01 times 10 to the 22 molecules of HNO3. All right, so hopefully you got that one right on your own. If you didn't get this one right, you're going to want to redo the second part because you probably also missed that. All right, so let's look at the second part. It says how many oxygen atoms are in this sample. So again, I can look at HNO3 and I can see that 1 molecule of HNO3 is 3 atoms of oxygen. For every HNO3, I get 3 atoms of oxygen. So I just take the molecules that I just calculated. So 4.01 times 10 to the 22 molecules of HNO3. And I follow the golden rule. Molecules needs to go on bottom. So 1 molecule of HNO3 is 3 atoms of oxygen. So my molecules cancel. Since both numbers are on top, I just multiply and I get 1.204 times 10 to the 23 atoms of oxygen. Now, every time you get a molar mass problem, it doesn't mean you're going to also have to use Avogadro's number. It just depends on what the question's asking. Sometimes you may need it, sometimes you might not. Sometimes you may need to go all the way to atoms, like in this one. Sometimes you don't need to. It just depends on what it's asking. So that's why reading the question is very important. Figure out what you're starting with, what you're going to. All right, so the next thing we need to talk about is volume. So Avogadro's hypothesis states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So at STP, 1 mole of any gas occupies a volume of 22.4 liters. Well, what is STP? STP just stands for standard temperature, which is 0 degrees Celsius, and pressure, which is 1 atm. So STP is standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atm. This is the abbreviation for atmosphere, which is a unit of pressure, not for atom. Atom does not have an abbreviation. So the volume of a gas changes with temperature and pressure. That's why it has to be at STP. So the 22.4 liters can only be used if a gas is at STP. If the gas is not at STP, we will learn later in chapter 14 how to do calculations for those. So we have another mole conversion factor, and that is 1 mole equals 22.4 liters. So we use this if the question talks about liters or volume. So see, now we have 3 conversion factors. We use Avogadro's number if it talks about atoms, molecules, or ions. We use molar mass if it talks about grams, and we use 22.4 liters if it talks about volume, and it's at STP. Because, again, like you can see here, this is a picture of balloons that were blown all the way up. Like this small light blue one used to be this big, and then it got really cold at night. You can see there was ice on it, and so then eventually that gas inside the balloon shrunk. So let's look at how to use the 22.4. Most people like this one the most because, as you can see, I gave you the number again. So you don't have to figure out the number like you do for molar mass. A lot of people like it more than Avogadro's number because it's easier to put in the calculator. So it says determine the volume in liters. So I see volume in liters, and that's how I know I'm using 22.4. Of 0.6 moles of SO2 gas at STP. So I'm going to start with 0.6 moles of SO2. So then I just follow my golden rule. Since I have mole on top, I'm going to put the 1 mole on bottom. And since I'm talking about volume in liters, 1 mole is 22.4 liters. So my moles cancel. Since both numbers are on top, I'm just going to multiply. And so once I multiply, I get 13.44. And then my unit is liters, and my substance is SO2. So see, this is why most people like 22.4 the best. It's clearly the easiest to use. All right, so let's move on and look at a couple other examples. So for these, you probably just want to go ahead and pause it and try both of them because these are pretty easy. So I'll assume you pause it and try the first one. So it says, what is the volume? So since I see volume, that's how I know I'm using 22.4. Volume of 3.7 moles of N2 at STP. So I start with my 3.7 moles of N2. So I follow my golden rule. Mole is going to go on bottom, so how many? 1 mole. And since I'm looking for volume, 1 mole is 22.4 liters. Like once you learn all 3 conversion factors, you just have to be careful to make sure you use them at the right time. So you got to look for those keywords like atoms, molecules, ions, grams, or mass, and volume or liters. All right, since both numbers are on top, I'm just going to multiply. And so when I did that, I got 82.88. My unit is liters, and my substance is N2. So hopefully you got that one right. Okay, I'm going to assume you've already tried the bottom one. So let's look at it together. So it says how many moles is in 127 liters of CO2 at STP? So liters is how I know I'm using the 22.4 this time. So I start with what I know. 127 liters of CO2. I follow my golden rule. So since liters is on top, this time I'm going to put the 22.4 liters on bottom. So again, you've got to be careful. Don't just look at what am I doing each time. Look at what the question's asking. So since I started with liters, I put liters on bottom. 22.4 liters equals 1 mole. So my liters cancel. Since one number's on top and one's on bottom, I'm going to do 127 divided by 22.4. And I end up getting 5.67 moles of CO2. All right, so hopefully you got those right. So let's move on and look at our section assessment. Oh, well first let's remind ourselves of our conversion factors. So now we have 3. So remember, we use Avogadro's number for atoms, molecules, or ions. We use molar mass if it says anything about grams or mass in the question. And we use 22.4 liters at STP if it says anything about liters or volume. So now let's look at the section assessment. So it says, what is the volume of 1 mole of any gas at STP? Well, it is 22.4 liters. All right, so number 2 says, how many grams are in 5.66 moles of calcium carbonate? Well, I see grams, so that is my hint that I'm using molar mass for this one. Okay, because the thing is on the test or a quiz or a worksheet, they're all going to be mixed up. It's not going to have a section where you use each part. All right, so you got to be able to figure out which one you're using. So grams tells me I'm using molar mass. So I start with what I know. So I know I have 5.66 moles of calcium carbonate. So I got to write my formula. So calcium is Ca with a positive 2 charge. Carbonate is a polyatomic ion. It's CO3 with a negative 2 charge. Positive 2, negative 2 cancel, so I don't need any extra subscripts. All right, so since I am doing grams, I am going to have to do molar mass. So let's go ahead and add that up. So I'm going to do 40 for the calcium. I'm going to do 12 for the carbon. I'm going to do 16 for oxygen, but I'm going to multiply it by 3. And so when I do all that, I end up getting about 100 grams per mole for calcium carbonate. All right, so once I know that, I just follow my golden rule. So since mole is on top, the 1 mole is going to go on bottom because we want to follow that golden rule. And then in this case, 1 mole is 100 grams for calcium carbonate. Because remember, every substance has its own molar mass. So then, since both numbers are on top, I just multiply, and clearly I get 566 grams of calcium carbonate. All right, and these mole conversions are super important because for chapter 12, we're going to be using all of this again. So you need to get good at it in chapter 10, so chapter 12 is a little bit easier. All right, so number 3, it says find the number of moles in 508 grams of ethanol. And then here I gave you the formula for ethanol. So again, my key term right here is the fact that I have grams. So I'm going to use molar mass again. So I'm going to go ahead and add up my molar mass. So carbon is about 12, but I'm going to multiply it by 2 since I have 2 of them. Hydrogen is 1, but I'm going to multiply it by 5. Oxygen 16, and hydrogen again is 1. So once I add up, I get about 46 grams per mole. So this time, 1 mole is going to equal 46 grams. So I'll start with what I know. Well, I have 508 grams of C2H5OH. So I follow the golden rule. Since I have grams on top, I'm going to put grams on bottom. So see here, I had moles on top, so I put the 1 mole on bottom. Here, I'm starting with grams, so I'm going to put the 46 grams on bottom. So again, it's all about just following the golden rule. And of course, 46 grams equals 1 mole, because all molar mass equals 1 mole. So my grams cancel, and so this time I have 1 number on top and 1 on bottom, so I'm going to do 508 divided by 46, and I end up getting about 11.04 moles of C2H5OH. Just like that. All right, so let's look at our bottom one. So it says calculate the volume in liters. So once I see volume in liters, I know I'm using everybody's favorite, 22.4. So I don't have to add up molar mass or anything. However, there's still an easy way for you to lose half credit on this problem. So let's look at it together. So it says of 1.5 moles of chlorine at STP. So I have 1.5 moles of chlorine. Chlorine is Cl. However, chlorine is one of our 7 diatomics. So when it's by itself, it is Cl2. Now I know you're thinking like, well, I mean, that's not going to matter. It's still 22.4. But if you put Cl as part of your unit, I count half off because that's not correct. All right, so I follow my golden rule. So mole is on top, so I'm going to put my 1 mole on bottom. And then, of course, that equals my 22.4 liters on top. So my moles cancel, so I'm going to multiply 1.5 times 22.4, and I get 33.6. My unit is liters, and my substance is Cl2. Okay, so if you just have this, 33.6 liters of Cl, I count half off because your units are incorrect. Okay, so just be careful of those 7 diatomics. They come back so many times. All right, and then last question. It says 3 balloons filled with 3 different gaseous compounds each have a volume of 22.4 liters at STP. Would these balloons have the same mass, or would they contain the same number of molecules? Explain. Well, let's look. They both have 22.4 liters, which means they both have 1 mole. Well, 1 mole always equals 6.02 times 10 to the 23 atoms, molecules, or ions. But 1 mole is different for every substance for molar mass. So since it has 3 different compounds, they're each going to have different molar masses. So this number would be different for each one. So they are going to have the same mass. And our explanation can just be 1 mole equals 6.02 times 10 to the 23 molecules. Okay, so that is always the same. But they'll have different masses because each of those molecules is going to have a different molar mass. All right, so in section 10.2, the important thing to get is how to convert to moles and molar mass, and then how to convert between moles and volume.